crap off. Today we're going to be talking about low charge specifically in cooling mode. I get a lot of questions about this particular mode, especially here in the state of Florida where we are dominantly in cooling mode. But here's something else I want to talk about, and this goes out to all of you guys out there who are constantly recording and sending data to your tech support guy, to your senior level tech, to your sales engineer. Yes, I know you guys exist out there. I do love you. Just recording 36 minutes of data and then sending it to them and saying, hey, here's all I got. Like, we got problems, but like, I got 26 minutes of data, man. Can you tell me what's wrong with it? Like, this is all I could do. I mean, 26 minutes, that's like a lifetime. I'm going to show you why more is better. Why recording more operational data is actually the best thing in the world. So let's dive into this one. So now, as you can kind of see, the data set here, we're in thermostat on. That's about all I have populated. We're in cooling mode. Okay, now I've zoomed all the way out. And so what we have here is we have a 2-hour snippet, which means that this person is recording every 20 seconds, which is a big no-no. You should not be recording every 20 seconds. You should be recording every 60 seconds. Clearly, they have not been watching any of these videos. So when we talk about cooling mode, I like to go back to the 3 pillars. What's the first pillar in the 3 pillars? Say it with me, right? Suction superheat. Okay, so I like to follow the path of compression. When I say the path of compression, in heating mode, I follow discharge superheat first, and I go on the leaving side of the compressor. But in cooling mode, I like to look at the beginning part right before the compressor. So we're talking about suction gas coming back down the suction line to your actual inverter compressor. And so suction superheat is the measurement of the quality of vapor returning back to the compressor. It tells me the quality in regards to, is it a liquid? Is it a vapor? Is there enough of it getting back to the compressor? All those things are determined with suction superheat. So what we do now is we take our suction temperature of our unit and we take our TE, which is evaporator temperature spelled backwards. With evaporator temperature, this is 91.9 PSIG in R410A converted to saturation temperature. That's how we get TE. If you didn't know that, now you know. So we look at this and we go, okay, well, let's get out of the rocky, bumpy starts here. That's probably, let's see, restart standby is right there. Okay, restart itself, that's okay. But also, this is probably just startup control, which isn't populated for VRV3. It's actually populated for VRV4 or newer. That's okay, I don't need it. I can see that it gets a little rough and rocky. So this is a 2-hour data snippet. So from here to here, let's say you just do 2 hours. Let's go back to the teeny tiny snippet that we just talked about before. So from 12:51 to 13:21, this is 30 minutes of data. Okay. Just let that sink in. So you guys out there who are sending people data and recording only 30 minutes of data, you tell me what you see in this data set, right? Okay. Let's see here. I can see suction superheat. Okay. It's fairly high. That's all I got. Okay. Well, maybe about discharge superheat. Okay. Heat exchanger gas temp. I could do inverter temp, but it looks like the compressor doesn't even run in this module. Okay, well, let's go to the other module. REMQ series, right? VRV3, there's always a pair. Okay, inverter discharge temperature. Let's look at let's see here, TC. Okay, so 147, 84, so that's about 60 degree discharge superheat. That's not terrible. Looks the same. Wow, look at all this information that we're getting. Maybe we go to system subcooling because, we're about to solve this puzzle here. We're about to crack this problem wide open with 26 minutes of data that you recorded just because, you didn't have the time to bother to actually do it. But that's okay. You're okay. We're good. Yeah, everything's fine here. Yeah, I'm not mad at all. Okay, system subcooling. We're at 70, 84, 14 degrees subcooling. This data set's perfect. Wow, no problems, no issues. So suction superheat, it's okay. It's 30, right? So it's in range. Subcooling 14 degrees, a little bit high, 11 degrees plus or minus 3. It's in range. 60 degree discharge superheat, also in the 60s, in range. There's no problem in this data set. And I would love to just take this data set and just hit you over the head with it because there is a problem in this system, but you can't determine that in 26 minutes of freaking runtime data. So again, if you're out there troubleshooting systems and you're only recording 26 minutes of data, just hang it up and go do something else. The VRF is not for you, right? Go back to working on package units, go back to working on split systems. I get it. R22 is the god of all refrigerants. I'm not going to dispute that with you. However, you've been doing this for 30 years and 26 minutes is all you think you need. And it's not. You're missing it, guys. You're missing it. So let's go back to our little thing here. Let's go back to the 2 hours. Okay. Even in 2 hours, what did that look like? We could go back and we could populate the same things again. Let's see here. I'm in the wrong module. Let's go back to the other module. Move my big old head out of the way here. Okay, it goes up a little bit, but even in a 2 hour window of troubleshooting this data, if we do both TC and TE, and we look at our discharge temp, okay, we got 82 degrees to 140, right? Not terrible. Still in the 60 degree range. Not terrible. Well, it gets a little higher. Okay. It's a little elevated, but it hasn't broken that 72 degree mark. And if it has, it's only by a small amount. Still not terrible. Suction temp, 70 degrees. TE, 79. It's a little bit more elevated. Okay. So now we're talking about a 40 degree suction superheat. I'm starting to get a little bit concerned, right? This is when I would call you and say, hey, I don't like what I'm seeing. This doesn't look good. How did you leave the system like this, right? Subcooling, it's gone up a little bit now. Okay, well, that's a little concerning. But we could also go back over to heat exchanger liquid temp. So, again, 2 hours of runtime data still is not enough data to troubleshoot this system. What would I do with someone send me something like this? Okay, look at indoor pulses, right? Go through the rest of the system, and I would still tell you, this isn't enough data, guys, right? 2 hours is still not enough. And I get it, right? I get it. It's difficult to get guys to jobs, especially in the middle of the day, and get enough recording on it. So leave it overnight. Come back to the client. Just pick up your laptop and go back, right? Again, we can make all the excuses in the world, but here's the thing. Do you want to fix the problem or not? Because if you want to fix the problem, then you understand what I'm telling you now, that you need at least 4 hours worth of data to troubleshoot this system. And in this snippet, of this data snippet, this is actually 6 hours of data. And this tells me so much about the system. Not 26 minutes, right? It's not this. It's this. All the way to the end. But this is a story, so let's paint the picture here, okay? Insufficient cooling. The system randomly throws a UO error code, and you're going to go, okay, it's low on charge. Okay, prove it. Prove it to me. How does that happen? So let's do the 3 pillars really quickly. Okay, suction superheat. What does it look like? Okay, we know that it's somewhat high and it gets higher. Okay, how does it progress over time? Not one snippet, not 2 snippets, not here, not there, not over here. No. What does it look like over time? So we go and we scroll and we scroll and we scroll and we scroll. And you'll notice at the end of my data snippet, wow, these lines are actually pretty far apart. They've gotten 2 gray lines apart. Now we're at a suction superheat of what? It looks like we're 80, 86 degrees and 30. That's 50 degree suction superheat. 56 degree suction superheat. That is very high. Okay. Notice how 6 hours later, it gets to the point where it's noticeable. And why is that? Oh, let's break it out. Let's break it out. Okay. Now I'm going to break out my 3D drawings here. VRV3, heat recovery. Dun, 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 dun. So a lot of you guys may know this, but VRV3 has what they call a refrigerant regulator. In this diagram, it calls it something different. It calls it a liquid receiver, right? And it is a liquid receiver. It's designed to receive liquid. But let's complete the refrigeration cycle here really quickly, and let's just cover it. What is the liquid receiver in VRV3? And where did it go on VRV4? We didn't go anywhere. In VRV4, we got rid of the liquid receiver and we put the liquid receiver on the liquid line. In here, this is actually what they would consider like a R410A tank disconnected from the circuit. So what's it designed to do in VRV3? And why does it matter? Because remember, when we have 20 tons of cooling, let's say 2 10-ton modules, upper and lower here, master and sub, you have to remember that we have 20 tons worth of capacity, 20 tons worth of compressors. An inverter and a standard, and an inverter standard. 4 compressors, right? Gang signs. 4 compressors. With the 4 compressors that we have here, you have to remember we have 20 tons of capacity. So what do you need? You need 20 tons of refrigerant to move that capacity. It's not just enough to spin compressors at 20 tons worth of capacity and moving refrigerant super fast. You have to have the refrigerant quantity to move that many BTUs. And so what do you do on a 20-ton system when only 2 tons of cooling is actually calling for capacity? Well, what you do is you take that refrigerant and you stack it in your liquid receiver. Again, Brian Orr did a podcast on why subcooling doesn't matter when you have liquid receivers and systems. Now you're going to say, well, that contradicts everything we teach here. And again, he has a point up to a point when it comes to VRF. And that point is exactly this. With VRF systems, we stack the liquid refrigerant in the liquid receiver. On VRV3, it was completely separated from the liquid line. And what happens is the solenoid on top opens up, right? We go from there, we pull in liquid into the top of this tank. At the same time, we then open this one up here. We purge the gas out of the top of this tank, back over into the suction line, and it fills this liquid receiver. In the process of filling this liquid receiver, we now pull the refrigerant from the actual system and stack it in this tank. And we can do that in both modules. We have one here and we have one here. That allows us to pull liquid refrigerant away from the system. Now, why does that matter? Because if the demand is low on the system, it's going to pull gas from the system. Okay, easy concept. Great, got it. What happens when the system is undercharged and it goes to add that refrigerant back to the system? Well, I'm so happy that you asked. It looks like this. Well, when your liquid receiver is full of liquid and I put a full demand on the system, what happens? It starts to empty the receiver. How does it empty the receiver? It opens up this bottom line here, right, and allows liquid refrigerant to trickle through a capillary tube back into the suction line, and it charges the system over time. This is why your 26 minutes of data can jump off a bridge, because I don't care. I don't want it. This is why 6 hours of data is going to show me the problem over time, because that liquid receiver is charging back to the system. And where are those solenoids at? Let me just show you. Ooh, I'd love to show you. You've got your EV bypass here. You've got other, let's see here, refrigerant regulator discharge, refrigerant regulator discharge, refrigerant regulator liquid, refrigerant gas purge. These are all your solenoids on that circuit for that system. Now they're off right now, but again, when the system modulates over time, it's going to empty that charge back into the system. And so don't be fooled that the charge looks okay in low demand, because it's, again, it has enough refrigerant for that low demand. But what happens over time? Well, over time, when it goes to pull the liquid back out of that receiver, if there is any, the suction superheat drifts, and it drifts so much that at the beginning here, we go from a 30 to 28 degree suction superheat all the way up to a huge 56 degree split of suction superheat. Now, I can even go as further as want to, and here we can go further here. Another key indication of undercharge on a system, 2,000 pulse valves, right? Wide open, not metering refrigerant. We've talked about this many, many times here. Valves that are wide open or all the way closed are problems. We're not getting enough gas to these indoor units. Now, everybody loves to go to the AEVs inside and say, yeah, 2,000 pulses. Yeah, 2,000 pulses means overcharge. And I just taught a class to our team here internal. When we talk about 2,000 pulses and we say that's overcharged, it is not overcharged in heating. It is a very bad habit to tell yourself that 2,000 pulses inside is undercharge. It's going to get you every time you look at heating data and you think 2,000 pulses undercharge. No, wait a minute. That doesn't make any sense. Wait, I thought 2,000 pulses means undercharge, but he's telling me that 2,000 pulses in heating is overcharged. So maybe I can't correlate one thing to both, because you can't. What you can correlate to both is high suction superheat, high subcooling, right? High discharge superheat. Those are things that we can measure that mean something every single time, right? Those aren't things that change based upon the mode. That's actually the quality of refrigerant within the system. And so high suction superheat, if I go to my sub module, you'll find that, okay, I've got 2 compressors on now. It is running full bore. And my discharge superheat is, it's not that bad. It's just 105. It's just 203 degree discharge compressor temp. Whatever, right? That's not terrible. That is terrible. That's awful. 56 degree suction superheat, high discharge superheat. And then guess what? It's even low subcooling. Okay, let's see the subcooling here. Outdoor heat exchanger liquid temp. Where did we go here? Oh, that's right. Here's the other thing that's going to get you, and I love talking about this. VRV3. Now we have that beautiful chart that I built. Yes, you are welcome. Daikin did not make this. I made this when I worked at Daikin. I did make it look really legit though, didn't I? This is VRV3 four-way valve operation. This is designed to help you troubleshoot these systems and the data. And why is it important and why am I talking about it? Well, I am talking about it because it is just too much to go back and forth between the service manual and the service checker and the service manual and the service checker and the service manual and the service checker. And I could say this a million times because I've had a lot of coffee. But I'm going to stop here. This chart I made so that I could print it off and I could not only tell what the temperature of the air coming out of the module is, right here, right? I even give you some nice little beautiful arrows. Look at that. That's a hot arrow. That's a cold arrow. Wow. I know, right? The things we think of. This lets you understand what four-way valve positions they should be in. In cooling mode, your dual gas line should be on. In heating mode, your dual gas line should be off. There should be hot gas flowing into the building. I even gave you refrigerant piping diagrams that are colored. Watch out. And so this is all dual gas right here. Dual gas section, top to bottom. Okay, that's everything you need to know about dual gas. Here is the master main four-way valve for the outdoor heat exchanger. Here's the sub outdoor heat exchanger main four-way valve. Why is this important? Because we're in 100% cooling mode right now in the data, but you're going to notice something. What are you going to notice? That's what you're asking me. What am I going to notice? I already noticed some things, but let me notice you noticing something else to notice me noticing it. You're going to notice here that although my two compressors are screaming in my submodule, that my heat exchanger gas temp is 71.6. What the F? Why is there no hot gas flowing through my submodule? And I'm going to tell you, because there's this beautiful thing called GR value that I'm not going to tell you about, but I'm going to mention it. There's a little plug. That when the system demand and also capacity and also pressures and also temperatures are of just the right type and size where the system doesn't have enough gas to maintain the system, what does it do? It says, hey, I don't need the refrigerant for this coil, so go ahead and disconnect it. So what happens? Outdoor EEV closes and then the four-way valve shifts. So it goes inactive. That's why there's an active and an inactive, right? This is normal operation. This is low demand or low capacity, low refrigerant charge. So it shifts the four-way valve over on the submodule because it doesn't need the coil, right? There's not enough refrigerant. What am I going to do with this? I'm not doing nothing with this. I can't do nothing with that. Get out of here. So it goes and it shifts the four-way valve over and it only uses the master. And how do we see that in the data? That's not a four-way valve problem. It's not a programming issue. And that results in right here. You can see it. Heat exchanger gas temp is 71.6. Okay, well, how does he really know that it's not using it? Well, because EEV pulses are at 0, bro. Come on, catch up. Where you been? Apparently someone hasn't been reading their service manual when they go to sleep at night. Also here, four-way valve positions, on. Now let's go back to the picture. What we notice here, inactive is on. It's not using it, guys. It doesn't need it. Why doesn't it need it? Because there's not enough bloody charge in the system to make it work, right? So where does that gas go instead? It goes to the actual master module. There it is. There's my hot gas. Why is that important? Because if I'm taking subcooling on a module where no refrigerant's actually flowing through the coil, guess what? Subcooling's pretty high. And it's not. Discharge superheat's high, suction superheat's high. Now let me do the subcooling on the actual module that has actual liquid flowing through it, and that's right here. 100 degrees with 100 degrees and 105, that is a 5-degree subcooling. But here's where I'm going to get you. Oh, I'm going to get you. You say 5-degree subcooling. Well, that's something. It's liquid. I mean, it's better than 0 degrees subcooling, right? But is it? How do we tell and determine the quality of liquid in a system? Well, it's subcooling, right? That's the answer. The answer is subcooling. You're asking a question you already have the answer to. But here's the thing. You would then turn around and ask yourself, okay, subcooling on the module, 5 degrees. Only using one coil when I should be using both coils because I have a 20-ton demand on the system. That's not great. Okay. I'll look past that. 5-degree subcooling on my master module. Okay. Now, the other ones are red flags, right? High suction superheat, high discharge superheat, red flag, red flag. Subcooling, 5 degrees, okay? Listen to me, look at me, look at me, look at me. Listen, 5 degree subcooling. What steps is your fan at? What? Can anybody answer that question? I don't think you can. Well, why does it matter? Why? Well, fan steps? Subcooling, bro. Okay? It's not. What do we need to make subcooling? Fan. You need a fan to move. You need air to move. Air to move. If air is moving, then fan's moving. Yeah, okay, that makes sense. So fan should be full speed. In VRV3, there's 8 steps. There's 0 to 8. 8 being the fastest speed. Usually 7 is the highest you'll see. 8 is, outside of demand limits. This thing should be full blast, 5 degree subcooling, right? There's not enough refrigerant in the system. What if we go down here and we look at the fan step? It's at 0. What does that mean? That means it's off. Wait, hold the phone. Submodule has got no gas. Okay, it's closed, shut down for construction purposes. We'll reopen in the spring. Master module is getting hot gas, but it's making 5 degrees of subcooling with 0 air flowing across the heat exchanger. It's magic, right? It's an ambient subcooler. That's what it is. It's new technology. Don't worry about it. It's too complicated. What is a dead giveaway for undercharge on systems? And now listen, people call me the VRV whisperer. Sometimes they've called me the guru. I hate titles. I'm just a technician. Stop calling me that. In a VRV real world scenario, I would walk through a courtyard, 20 modules, VRV3, on a roof, on the ground, it doesn't matter. Hot day, middle of Florida, right? Middle of Florida. Well, it is middle of Florida. Okay. Middle of Florida, middle of summer. There we go. Let's say it's 90 degrees, peak temp for that day, 92 maybe. Everything's in full cooling. And I could walk past a condenser where the fan would be off on one module and turning on and off. And this is what we see here. Off, on, off, on, off, on, off, on, off, on, off, off, on. This looks like square waves on an oscilloscope for VRV comms. This is fan steps. 0 is off, 1 is on. Off on, off on, off on, off on, off on. And then the other module, the fan never runs. Because again, no refrigerant's flowing through it, so why would it run? This is a dead giveaway on an undercharge scenario. And notice that it's only when I get to the end of my data after 6 hours, not in the 26 minutes I told you don't do. It's only at the end of the data that I see it, right? Look at all this sporadic fan on, off, on, off, on, off, on, off. Fan speeds will also allow you to troubleshoot systems to determine if there was an issue. If you walk past the system and the fan is on, off, on, off, on, off, and the other module is not running and it's the middle of summer and you know that system should be working its butt off, it should be a red flag in your mind that, hey, I'm here to look at that error code, but that system is low on charge. And I can hang my hat on that every day. And people would think, well, oh my gosh, he's the VRV whisperer, right? He can hear them off in the distance crying for help. No, it's because I know from troubleshooting so many systems like this that when the fan does this and the system looks like that, it is undercharged 100% of the time. And it is very low on charge. And this system was. The system was actually 45 pounds light. So again, discharge superheat, suction superheat, system subcooling, all of those things are tools in your tool belt. But sometimes once you get that solidified, maybe you want to seal the deal. Maybe you do have 6 hours of data and someone has blessed you because technicians actually listen and watch these videos. When you do something like that, you catch something like this. And if you catch something like this is 100% undercharged, and you have all the information you need at the end of the data set to tell you that. If I go back to the beginning, remember, in the 26 minutes that I looked at, it was good discharge superheat within range, good suction superheat within range, subcooling within range, and guess what? I mean, the fan wasn't running, which is kind of a red flag, but again, you can't troubleshoot in the first 26 minutes. This is an overtime, how does it progress? And it gets worse, and it gets worse, and it maintains with no fan speeds running. This system, again, undoubtedly undercharged. So if you're out there watching these videos, first of all, I apologize that you have to bear through 24 minutes to hear all this stuff. But 2, don't ever take anything off the table. I don't ever want to see technicians take a value, a number, and hit it aside their head and say it has to be this. This is always this, because it's not. VRF, that's what VRF does. VRF is really good about taking what you think you know and proving to you that you have no idea what you're doing, and neither does it, right? VRF doesn't make sense, and that's the beauty of it. It's the chaos, right? Thriving in the chaos. Data is chaos, And so if you have a small inclination of what you think is supposed to be that, you're going to look for it. And when you don't find it, you're going to feel lost. So you have to be like me and just go crazy, just go mad. And when you go mad and you let go of all your inhibitions, no, wait a minute, that's the wrong video. Don't ignore that. You let go of everything that you know about refrigeration except for the three basic pillars: suction superheat, discharge superheat, and subcooling, and then work the problem. Work the problem as if you've never seen it before and you're just trying to understand the science behind it, right? If I'm making 5 degrees of subcooling, how fast is the fan running, right? And again, it goes back to the same thing. If I have a unit that's in heating and my superheat across my outdoor coil is just really, really low, is my fan all the way up? Yeah, it is all the way up. Okay, well, then something's restricting the outdoor coil to get airflow across it, right? Or the system's overcharged. But again, I can't just say pinched off pulses, low superheat, fan at full speed. Oh, it's overcharged. No. Come to find out, no one set the high fan static setting speed, right, on the unit, and they put snow hoods on it. You have to set the high fan static speed setting on that unit specific. Because again, when you add ductwork to it, when you restrict the volume of air that can get to the coil, you have to increase the fan speeds. Otherwise, you're going to get insufficient airflow across the coil. That's basic refrigeration. But again, you can't just take one thing and say, when this happens, it's always this. Remember, there's 3 pillars, not one, right? There's not just one number that we memorize and it hits the nail every time. No, it's 3 numbers that we use not to make a diagnosis. We use these to know where to go next, right? We've got this giant board of problems and scenarios, and this helps us just kind of hone in on where to go next. I need to go here. I need to go look at fan speeds. I need to go look at indoor valve pulses. I need to go look at the subcooling circuit. I need to go look at the accumulator. I need to go look at the submodule, right? I need to go look at the discharge temps. This is where it's going to point you. It's a compass. So use it as a compass, not as an anchor, right? We're not just throwing it into a report and saying, yep, she's overcharged. Now, they are good numbers to use to dive down into that to say that's what it is. But again, we have to understand what we're looking at, what we're doing, why we're doing it, and never make assumptions, right? I'd love to say assumptions kill, but I think that's actually from the Jack Reacher series on Amazon. So I'm not gonna say that. It's not my catchline. Okay, so now you know this is extreme undercharge. Again, these numbers over time. Don't get 26 minutes of data, 6 hours, 4 hours, anything. More is better, right? Someone sent me 172 hours of data the other day, and I loved it. It painted a beautiful picture. It's a little overkill, but it's still good. So, all right, that's what you get. I appreciate it. As if I'm like doling out a punishment here. I'll see you guys on the next one. Thanks for watching.